Hi there, in this video we'll discuss section 24.1, Goodness of Fit Tests. In this chapter we're going to be working with categorical variables. In earlier sections we looked at how to test hypotheses about a single proportion as well as the difference between two proportions. Now we consider entire distributions. The question we'd like to answer is this. Is an observed distribution consistent with what we expected? A goodness of fit test applies to a single categorical variable, and it involves testing a hypothesis. We specify a model for the distribution and want to know whether it fits. So let's look at an example. Suppose I roll a standard six-sided die a number of times, and based on the results, I'm skeptical that the die is fair. We could set up a hypothesis test to see if we have evidence that the die is really not fair. The null hypothesis is that all faces of the die are equally likely to occur. In other words, the probability model is correct. The alternative hypothesis is that not all faces of the die are equally likely to occur. The goodness of fit test assesses whether the observed results are consistent with the null hypothesis model. So let's suppose I roll the die 36 times. I just used an online site to do this. So I had it roll the die 36 times. Here are the outcomes. So I'll record those in a table here. In the top row, we have the 6 possible outcomes from rolling the die. And then in the second row, you see how many times each of these occurred. So a 1 was rolled 7 times, a 2 was rolled 6 times, and so on. Notice a 3 was only rolled 2 times. And that's the reason why I'm a little bit skeptical that the die is fair. Just like with our other hypothesis tests, we have a few assumptions and conditions to check. The first is the counted data condition. It says the data must be counts for the categories of a categorical variable. And here we just want to make sure we're not reporting proportions or percentages or something other than counts. And of course, if we look at our table, we've just reported counts for each of the possible outcomes. The next assumption is the independence assumption. It says the counts in the cell should be independent of each other. The best way to check the independence assumption is by showing that the randomization condition holds. This says we have a random sample from the population of interest. For our example, I had the online site randomly roll the die 36 times. The final assumption is the sample size assumption. Here we need to check the expected cell frequency condition. We should expect to see at least 5 individuals in each cell. Now this is referring to the expected counts, not the actual or observed counts. For our example, we rolled the die 36 times. The likelihood of each outcome is 1/6, so we would expect 6 of each outcome. And that's certainly at least 5. I should point out the expected counts don't have to be whole numbers. Oftentimes they're decimals. It just worked out that they were whole numbers in this case because we did a sample of 36. So next we'll calculate a test statistic. It's called the chi-square statistic. And the way we do it is we take each observed count and subtract the expected count. That's referred to as the residual. Then we square it and divide by the expected count. Finally, we'll sum over all cells. So for us, it looks like this. We rolled a 1 7 times, that's the observed count. We'll subtract the expected count of 6 square it, and divide by the expected count of 6. So we'll do that for each outcome. Sum all of these, and we get our test statistic chi-square is equal to 4.67. We need a new family of models called the chi-square models. These models, unlike the normal model and the student's t-model, do not measure distances in standard deviation or standard error units, cannot take on negative values, and are skewed to the right. Before, if we got a test statistic value this large, that would have been a big value for z or t, leading us to reject the null hypothesis. The family of chi-square models, like the student's t-models, differ only in the number of degrees of freedom. Here's how we compute that. We take n, which is now the number of categories for our categorical variable, minus 1. So we're not using the sample size. For the die rolling example, the number of categories is 6, so we have degrees of freedom equal to 6 minus 1, or 5. We can see some of these characteristics I was talking about if we look at a couple of chi-square curves. One has 5 degrees of freedom, the other one shown here has 9 degrees of freedom. You can see that they're skewed to the right, and notice both the shape and center change as the degrees of freedom increases. Once we have our chi-square test statistic, we can use technology or a table to compute a p-value. So I'll illustrate both here. I've got a link to a p-value calculator in our Canvas page. It looks something like this. So we'll enter our test statistic value, 4.67, specify the degrees of freedom. For us it was 5. And then it asks you to specify a significance level. I chose 0.05. We'll see here that it really doesn't matter in this case because we get a fairly large p-value of 0.457465. Of course, that p-value is greater than 0.05 or any of these standard significance levels. Now you can also use a table, and what you need to do is go to the row corresponding to your degrees of freedom. So for us that's 5. And you want to trap your chi-square value between some of these specified values here. Well, for us, our chi-square value is lower than this first one, and so our p-value must exceed 0.1, and that's what we saw using technology. Based on our p-value, we can say the following. If the null hypothesis is true, in other words, if in fact all faces of the die are equally likely to occur, an observed chi-square value of 4.67 or higher would occur about 46% of the time. Our p-value is roughly 46%. This certainly isn't unusual, so we fail to reject the null hypothesis. These data show virtually no evidence that not all faces of the die are equally likely to occur. Just a word of caution, we simply fail to reject the null hypothesis here. We can never confirm that a theory is in fact true. The most we can hope for is to get some evidence against the null hypothesis. So that wraps up our discussion. I'll see you next time.